Hey everyone, welcome back to the Embedded Dude, and welcome to part 2 of the series How to Debug Your Embedded System. In part 1 of the series, we have been looking at emulators and on-chip debugger. In part 2 of the series, we will be looking at pins and tools to use together with them to make this method really powerful. We will also be looking at print statements, I guess everybody's darling these days, and core or crash dumps. So let's get into it.
A quick sponsorship statement. All tools and equipment you see in today's video have been purchased by me with my own money and are not in any way sponsored by anyone. I'm also not getting paid or getting products or services in exchange for my opinions and thoughts in this video.
Okay, so let's look at the next debugging method, pins. In the last episode, I said that on-chip debuggers are adding a cost, even though it's little. So let's look at an example where this plays a role. Here we have the Part2 PMS 150C, or also called the famous 3-cent microcontroller. Actually, I think it's cheaper than 3 cents. Spoiler, this microcontroller does not support on-chip debugging, but let's look at the specs. So it's an 8-pin microcontroller where 6 pins can be used as I/O. It's a RISC architecture running at 16 MHz. It has 64 bytes of data RAM, a 16-bit timer, 1 kiloword of one-time programmable memory. It can generate 8-bit PWMs and other things. So how do we debug this thing if it doesn't support on-chip debugging? We don't have that many options. We can buy a socket and a bunch of these PMS 150Cs. And whenever we make a mistake, we have to throw one away. Of course, we can spend one of the 6 I/O pins available as a pin for debugging. It's costly, but definitely if the application allows it, a good way to debug. We can connect this pin to a logic analyzer or oscilloscope to get the most out of it. Of course, we can connect an LED and have a visual indication, the classic hello world. Using a pin is usually a cheap option. Usually we are looking at microcontrollers with way more pins, and they are not one-time programmable. Pins are powerful, and combined with a logic analyzer or oscilloscope, it's a very good option. Obviously the disadvantage is that we have to use a pin and we have to have it available. It's always nice if you have debug pins planned into the first prototype hardware design, at least while developing the product. When looking at pins as debugging option, we should also look at the tools that make this way more powerful, like logic analyzers and oscilloscopes. A good place to start looking for logic analyzers, especially when you're on a budget, is SIGROC. They have made a software called Part2, which is open source, cross-platform, and it supports a variety of different hardware devices. So you just need to download it and install it, depending on which operating system you are using. Cross-platform, and then you have to choose a device that you want to use. So right now they're supporting 254 devices, and if you look at logic analyzers, you can see there's quite a bit of different devices that you can choose from depending on what you need. So as an example, I've chosen this one from SparkFun, a very simple cheap 8-channel logic analyzer for around $20. Compared to the other logic analyzers that we will be looking at, it has limitations, but it can do already a lot for $20. So you can decode your digital signals. So for example, if you're looking at UART, I2C or SPI communication, you can decode those signals with the software. And then of course you can use that to visualize your pins that you're toggling. You need to be careful that this one does not support 1.8 volt logic levels, but other than that, if you're working with a 3.3 volt or 5 volt system, you're good to go. So how does Part2 look like? If we look at Part2, and here this is the Part2 software, and here you can choose your device. I will choose the demo device just to show how analog signals and digital signals are getting captured. So if you just run this demo, so now it's stopped. You can just zoom in into the signal, and then you can see, of course, the analog signals here that have been captured and the digital signals. This should not be a tutorial for pulse view, but you can use cursors to measure how long a pulse takes, for example. So if you combine that with your pins that you're toggling in, let's say, a critical code section, you can see when this gets executed and how long it takes. Quite useful. And then, of course, you can, if you want to decode your digital signals, for example, let's say you're using I2C, then you can, that's just an example, but let's say the clock is on D0 and the data line is on D1, which is probably not true here, but then you could decode your I2C signal or SPI. It supports a bunch of different decoders here, so very useful tool for only $20. If you need a more advanced logic analyzer, then we have to look at some more pricey models. So here I've chosen a Salier logic analyzer, which is quite famous, and I think a lot of people are using them. They come in 8 and 60 channel versions. They support way higher sampling rates than the one we have been looking at before. They support voltage levels down to 1.2 and 1.8 volt. So you're not limited to 3.3 and 5 volt systems. They're supporting analog inputs depending on the version 10-bit or 12-bit. They have an excellent software which is called Logic. I like it a lot, and we will be looking at it a little later. They are not that cheap. They are starting at around $500 and go up to $1,500 for the Pro version. If you have a need for more advanced analog measurements, you need to go to a real oscilloscope, a mixed signal oscilloscope. Here I have chosen the picoscope. It doesn't have a built-in display, so you are using your PC with the software to display the signals. The advantage here is that you can use real oscilloscope probes, meaning you can use high voltage probes, you can use current measurement probes, you can use differential probes, everything that you can do with a real scope. The analog input measurement is way more advanced, so it ranges from millivolts to high voltage 700 volts depending on the probe. As said, you can do current measurements. It includes a logic analyzer. Usually these scopes and even more advanced scopes come with an advanced trigger system and much more. The cheapest one starts at $140, even cheaper than the cheapest Salier logic analyzer. So let's wrap this up. What is great about pins? Well, first of all, they're easy to implement. It's easy to toggle an LED or blink an LED when something happens in your code. You can also bit bang out a bit pattern and visualize it with a logic analyzer. That is quite cheap to do. All you need is an I/O pin. They do not require much memory. Some memory is of course used for the code to be executed. They are quite powerful in combination with logic analyzers or oscilloscopes. What to keep in mind? They're not able to halt the execution of your program. Don't overdo LEDs. They easily become a Christmas tree and you cannot tell which one was supposed to tell you what. They create minor latencies when your debug code to toggle the LED or bit bang out a pattern gets executed in between your application code. Alright, let's look at the next debugging method, print statements, or Printf. The famous Brian W. Cunningham has said the following.
The most effective debugging tool is still careful thought, coupled with judiciously placed print statements.
And who can argue with that? So how do we get the print statements out of our embedded device? So let's look at the ESP32C6 dev kit as an example setup. When adding a print statement to your code, the characters will be sent usually over a serial line out of the microcontroller. What we need is, we need a converter between the UART port of the microcontroller and the USB port on our PC. Quite often we have to use an external USB to UART bridge as shown below. But on the ESP32C6 dev kit, this one is already integrated. So the USB-C port that is marked as UART is connected to that bridge, which is then connected to the C6. All we need to do is to connect this USB-C via USB to our PC And on our PC, we have to run a terminal software that can monitor the characters being sent from our device. On our PC, the UART USB bridge will pop up as a COM port, which we can then use in one of the terminal programs, for example PuTTY or TerraTerm. Of course, we need to make sure that the communication settings on both ends are set to the same, meaning baud rate, data bits and stop bits have to be the same on both ends. Let's quickly look at some example code. Let me explain the setup that I have on my table right now. Here you can see in the middle I have the Salier logic analyzer that is connected to the ESP32C6 dev kit. The ESP32C6 dev kit is connected via the USB UART bridge to the PC, where we can log the print statements. On the PC I have also running the logic software that is connected via USB to the Salier logic analyzer. On the logic analyzer I have 3 pins connected to the dev board: ground, and then 2 digital inputs, D0 and D1. D0 is connected to pin 8 of the board and D1 is connected to pin 4 of the board. So let's look at the code. Okay, let's have a look at the simple code I have written. Up here I have defined the 2 pins that are connected to the logic analyzer, pin 8 and pin 4. I have defined a 500 milliseconds delay for the main loop. I have defined some debug data that we're bit banging out. In the main loop, we have a main counter that is just getting incremented every round. Here we are initializing the pins as output pins, and then we're jumping into the loop. We're incrementing the counter and toggling pin 8. Then we're printing our statement, including our counter value, and we're toggling pin 8 again. Then we're sleeping for 500 milliseconds, and we're bit banging out the data defined above. So the bitbanger function is actually quite simple. It bitbangs out the MSB first and then the entire byte. And down here we are having the toggle pin function. So quite simple. Let's flash that into the C6. Okay, done. So now I could use TerraTerm or PuTTY to monitor the serial output, but I can also use the ESP-IDF monitor that is built into that IDE, which is quite convenient. So I will start that one. And now we can see the printf statements being received on the PC over the serial line. So let's look at logic. I have only enabled 2 digital inputs, D0 and D1. All the other analog outputs, inputs and digital inputs I have disabled. So D0 is pin 8, which I call printf measurement, and D1 is a debug bitbang pin. So let's start this one in, and I will zoom out as we are measuring and capturing data. And as you can see, every 500 milliseconds we're getting events. Okay, so zooming in, we can actually see that the code, the printf code, takes 115 microseconds. So printf is not for free. We always have to keep that in mind when we're adding printf statements to our code. It impacts the latency of our code. If we are looking at the bitbanger function, we can see the bit pattern that has been defined being bitbanged out. So that can be quite useful to bitbang out different types of messages. But you need to be careful with this method because the bit timing here does not necessarily need to be the same all the time, depending on if you have interrupts interrupting the function or if you have FreeRTOS running.
Okay, let's summarize this. What is great about printf or print statements? We can print a lot of human-readable data, including variable states and different things. It's very easy to implement. It does not stop our code execution. What to keep in mind when using printf statements? Latencies need to be considered. Printf is not for free. You need a serial port. UARTs on a microcontroller are a scarce resource, so you might not have one available. The printf function itself requires memory. Consider something around 5 to 10K of flash memory. Alright, let's take a look at the next debugging method, core dumps, or sometimes also referred as crash dumps, system dumps, or memory dumps. So let's look at how it works and how it can help us to find bugs in our code. Core dumps or crash dumps are generally used as so-called post-mortem analysis techniques, meaning we already messed up, the damage is done. An unrecoverable software error has been detected. For example, an illegal instruction has been detected and the system is about to reboot. At that point, before we reboot, that is where we can take a snapshot of the system by collecting useful data such as CPU registers, thread or task information, stack states, and other memory content. That information can then be either printed out via a serial port or it can be stored in some available memory for a later download. That memory can either be the internal flash memory of the microcontroller or some kind of writable external memory, so that the crash snapshot data can be downloaded for analysis after the system has rebooted. In any case, we need a communication interface to get the data. The core dump functionality is basically a piece of software that you have to flash together with your application code. So let's look at an example. Alright, let's look at some simple code that will crash. Here we have our main loop, which calls this local function called countdown every second. In countdown we have a static variable that gets decreased every second. From 5 we're counting down to 0, and when we hit 0 then we have a divide by 0 exception, and then we crash. So in order for that to work, we need to have the core dump software compiled, and we can configure the IDF SDK either with this editor, or we use the idf.py menu config. And what we have to do is we have to configure the core dump functionality. So here I've chosen the destination to be the UART, so it prints it over the serial line instead of storing it in the flash. I've chosen the ELF format, which contains more information. I limited the number of tasks to be collected to 5. It's a very simple application. I decided to give the core dump functionality its own stack, so when it crashes, it doesn't use the stack of the task that crashed. And I decided to have the IDF monitor actually decode and show the summary of the ELF file automatically. The other thing we have to do is we actually have to configure the panic handler. So when we have that panic handler being invoked, I wanted to print the registers and halt and not reboot, so it will just sit there and wait. Alright, so it has been flashed, and if I now start the monitor, it will reset and reboot the microcontroller and start from scratch, and now you can see the countdown is running. And it crashed. So now we have the panic handler already printing some information and initializing the core dump. And now the core dump data has been received. So we can see that the core dump has been written via the UART. We can see how many bytes of the stack, of the core dump stack, has been used. So out of the 2,672 have been used. The core dump checksum. We could also store this information to a file, but yeah, I keep it in the terminal. So we can see the different memory regions with a name, address, size, and attributes. And if we scroll up here, we can see, actually let's go all the way up where it starts. So we have here where it says ESP core dump start. This is where the core dump data starts. And let's take it from the top. So here we have the thread registers, and we can see the exception cost being 0.6, which means integer divided by 0 course. We have thread infos, program counter, different register values, and then we can actually see where it happened. So we can see it happened in line 27, yes, of the core dump C file. And then we have the information about the task control blocks of every task or thread. So this one, I guess, would be the main, but there's no information collected for whatever reason. This one, I think, should be the idle hook of the FreeRTOS ESP timer, and you can see actually the call stack of these different threads listed here. Yeah, in this particular case, I think if we look at the panic handler, which started here, the panic handler already told us what happened, integer divided by 0, and already printed the registers, the core registers, and it also gives us a backtrace already. So just the panic handler could have helped us to find the issue, but if we have a more complex system, more complex software, the additional software we get through the core dump can help us to find our bugs. I think that's it, and I hope it was helpful. Let's quickly look at the size of the core dump software when we have to flash it into our microcontroller. Here I have the command prompt open, and I'm in my project folder, and if I use the IDF pi with the command size components, it will print out the size of the different components which our application software is made of. And if we look at the core dump, which is here, then we can see it occupies 11,604 bytes of flash. So it is not that small, so we have to keep that in mind. So let's wrap this up. What is great about core dumps or crash dumps? Well, first of all, it's a good method for post-mortem analysis. When the damage is already done, we still have the chance to analyze what happened. This method does not stop code execution, like a breakpoint would do. What to keep in mind when using core dumps? The core dump functionality requires memory. The expressive implementation takes around 6K of RAM and 11K of flash. We need to get the data out of the microcontroller, so we need to use some communication interface, usually a UART. If we want to save the snapshot data in a non-volatile writable memory, then we also need to reserve some space for the snapshot data. So that's it for part 2. Stay tuned for the last part, part 3. If you like that type of content, then please smash that like button and subscribe to the channel. Thanks for watching, and see you in the next one.